In this next section, which is module 23.4, we're going to look at these concepts of the vector potential, of the potential energy and of the electric potential from a slightly more sophisticated point of view. You recall we're going to be working now on 23.4, and this is the vector calculus or mathematical form of these for those of you who are more familiar or comfortable with calculus and a more exact definition of these concepts. You recall that we just determined that the potential energy U between two particles was going to be kq1 q2 divided by r1 minus r2 magnitude. And this is not a vector equation, it's a scalar equation, and this tells us that this was in section 23.2, that the energy of collecting two charges together, q1 and q2, at positions r1 and r2 as vectors, depends upon just k, which is 1 over 4 pi epsilon naught, charge of the first times charge of the second, divided by the distance between them squared. And this is just a magnitude. If we have many particles, then we can perform a sum over all I and j particles, like this, or this is I and this is j, and sum over I and j, but when we do that, we count doubly, and so we must take a 1/2. And we've already discussed this in that section. This is the potential energy of a collection of charges, how much energy it takes to bring them all together. And that can be positive or negative. If we bring a positive and a negative charge together, we're going to get energy out of the system. So it doesn't take a positive amount of work, it takes a negative amount. Then we also discussed in section 23.3 the electric potential. And the electric potential, V, which is measured in volts, whereas this is measured, you recall, in joules, is the potential energy due to divided by a charge Q naught that is required to give how much energy is given when this charge Q is brought into the system. And in other words, this will be for a single charge that's in that's already there, kq divided by the distance r away from that charge. So if we bring a charge Q naught up here, it'd be Q naught times the distance from Q naught, and so we can write this as the voltage due to a single charge in this way. Single charge voltage is measured in volts. And voltage is something we're all familiar with. Now, how do we see this in a more mathematical point of view? From a more mathematical point of view, we can talk about the potential energy or the work as the infinitesimal work, which is the force times the infinitesimal distance that we're going to move with that force. And you recall that the force is minus Q that we're going to have to exert is going to have to be against that charge. So it's going to be minus Q1 E, that's the force, times dr. And this is a dot product between these two vectors, just as the force is the dot product between F and dr. I should write that in a vector form there. And so this is going to give us minus k q1 q2 dr12 over r12 squared. Now if we integrate this, we'll get u is equal to the integral of this, which is minus k q1 q2 integral of dr12 over r12 squared. Now if I'm going perpendicular to r12, I do no work at all, so it's only when I'm going in the same direction, so I can remove the vector quantity associated with this and do a simple integration. This is r to the minus 2 dr, and you remember that the integral of x to the minus 2 dx gives us a negative sign, which will cancel this one, and just gives us a 1 over r. So this would give us, between these two limits, k q1 q2, exactly as we see here, divided by r12, which is r12 to the first power. So this is equal to the potential energy when we do it in a more formal way using vector calculus. potential energy of two charges. Again, that unit is in volts. Now, it's interesting to point out that since the voltage is, let's write it as dV, is equal to minus E dotted with dR, that's the infinitesimal voltage that we have. Why? Because it's like the infinitesimal work divided by the infinitesimal charge. So if we think of it, make a comparison of this formula with du is equal to minus F dot dr, then we see we can divide both sides by Q, and the force per unit charge is the electric field, whereas potential energy per unit charge is the voltage. Now, given this equation, we can divide through, of course this is the dot product, and so if we think in one dimension first, and then just write this as Ex dot dx, so I'm going to change that now to dV is equal to minus Ex dot dx, and make this a one-dimensional problem. Then you can see that if I divide through by dx, I get Ex, the electric field in the x direction, is dV over dx. Okay, that's just the electric field in the x direction. So if we look at the electric field in the y direction, it would be the change with respect to y. Those changes with respect to x, y, and z are called partial derivatives. So in general, we can write the equation E as a vector is equal to partial v with respect to x, and that, excuse me, there is a negative sign here, comma, minus partial of v with respect to y, comma, minus partial of v with respect to z. This function occurs so much in vector calculus that it's given a name. If we factor this v out, we can think of this as a differential operator, which we call del, or the gradient operator, times v, and that gives us the electric field. This is the inverse equation right here to the equation that we had up here, computing what v was as an integral of E dot dr. And this del operator here is very important in vector calculus. The del operator is partial with respect to x, partial with respect to y, partial with respect to z. And there are three kinds of, those are the components. So when it acts on something, the x component of the thing it acts on is partial of that quantity with respect to x. So there are three things in vector calculus that become very important. One of those is del dot a scalar function, which is, well, let me just write it as v, because that's what we have here. The next is where we take del dot some vector, and so we take the dot product, so this becomes the partial with respect to x of ax, and so forth. Then we can have del cross a vector, where we have actually, this is called the divergence of the vector field, and this is called the curl of the vector field. All three of these are enormous importance in vector calculus, and here we see the first one of these. The electric field tells us how this function, the potential, is changing in the x, the y, and the z direction, and this is a negative sign telling us of the relationship between that force and the direction. And this covers all of this section now.